Welcome to the deep dive. So, you want to talk about quantum computers,
You know it.
specifically how we might use those mind-blowing machines to uncover brand new particles.
Right. Diving into the really big questions today.
Exactly, and we're dissecting a research paper to do it, of course.
Always a good time.
This one's called Unsupervised Event Classification with Graphs on Classical and Photonic Quantum Computers.
Catchy title.
Right. Don't worry, though. We're about to make this way more exciting than your average physics lecture.
Absolutely. We're talking about potentially rewriting our understanding of the universe's building blocks here.
Exactly. Who wouldn't be fascinated by that?
Seriously?
So let's set the stage a little bit.
Sounds good.
This paper is tackling a challenge that sounds simple,
Okay.
but is anything but. How do we know if a particle collision, like the ones happening at the Large Hadron Collider, creates something genuinely new,
Okay.
or just more of the usual suspects we already know about from the standard model?
Right. So it's like looking for a needle in a haystack, but with particle collisions.
That's a fantastic analogy, because it's not enough to just smash particles together.
Right.
We need a system to tell us if anything interesting happened.
Exactly. And that's where this research comes in.
Okay, I'm intrigued. Walk me through it.
So imagine trying to find a single, tiny, unique grain of sand on a beach, but after a massive storm.
Oh, wow.
It's about sifting through an overwhelming amount of data and pinpointing the truly unusual events.
Wow. Okay, so how do we even begin to do that?
That's where unsupervised learning enters the picture.
Okay, now you're speaking my language.
It's like giving a detective 1,000 fingerprints,
Yeah.
then sneaking in one that's completely new.
Okay,
They might not know who it belongs to, but they'd know it's something they haven't seen before.
right. They know it's not a match.
Exactly.
That's a great way to put it. So the computer essentially teaches itself what's quote-unquote normal,
Right.
and then raises a flag if it encounters anything that deviates from that pattern. That's so cool. But here's where it gets really wild. This paper represents all that complex particle collision data as, wait for it, graphs.
You heard that right.
Like the ones we used to doodle in math class.
Exactly.
I did not see that coming.
So each collision is transformed into a graph,
Okay.
with the particles represented as dots and their relationships as the lines connecting them.
Okay, I'm intrigued. I have to ask, why graphs, though? What's the advantage of visualizing the data this way?
It's surprisingly elegant.
Okay.
Graphs naturally mirror how particles interact in the real world.
Okay.
By representing the collisions as graphs, we can use the tools of graph theory,
Okay.
which is a whole branch of mathematics,
Yeah.
to analyze their structure and search for anomalies.
So it's like they've found the secret code hidden within the collisions themselves.
Right.
And graphs are the key to unlocking it.
Precisely.
This is blowing my mind.
And it gets even better.
Okay, there's more.
The researchers didn't just draw these graphs and call it a day.
Okay.
They analyzed them using two main approaches.
Okay.
First, they used classical computing methods to establish a baseline. Think of it as analyzing the graphs with a trusty magnifying glass.
Okay, so that's the tried and true method.
Right.
But I'm guessing it gets a lot more exciting.
You bet. They then brought in the big guns, a photonic quantum computer.
Okay, here we go.
They used something called Gaussian Boson sampling to tackle these graphs.
Whoa, hold on. Gaussian boson sampling. That sounds like something straight out of Star Trek.
You're not far off.
Oh, wow.
Imagine a Rube Goldberg machine,
Okay.
but instead of marbles, we're talking photons, particles of light.
Okay.
That's Gaussian boson sampling in a nutshell.
Wow.
It's a way to analyze the graphs by encoding their information onto these light particles and then observing how they interact with each other.
Wow. Okay, so they're shining light on the problem, literally.
It's a bit more complicated than that,
Okay.
but you've hit on a key point. Photonic quantum computers are built on manipulating light, which has some fascinating implications compared to other types of quantum computers.
Oh, okay.
But we can get into that a little later,
Now I'm dying to know.
of course.
What did they find? Was all that quantum computing wizardry worth it?
It's promising, for sure.
Okay.
We're still in the very early stages of quantum computing,
Right.
and even simulating these experiments requires immense computational power.
Right. It's not like there's a quantum computer just sitting in a lab somewhere ready to solve all our physics problems.
Exactly. But that makes these results even more exciting.
Okay.
So they decided to focus on a specific type of particle interaction.
Ooh, even more intriguing. What kind of particle interaction are we talking about here?
They zeroed in on collisions that produce a Z boson.
Okay, remind me what those are again.
That's a fundamental particle associated with the weak force,
Okay.
one of the 4 fundamental forces of nature.
Right. The weak force isn't that responsible for things like radioactive decay?
You got it.
Okay, so that's a pretty big deal in the universe.
It's huge.
So they're looking at these Z bosons, and what? What are they hoping to find alongside them?
That's where it gets even more interesting.
Okay, lay it on me.
They're searching for evidence of a hypothetical particle that decays into others.
Okay.
And they're specifically focusing on collisions,
Hmm.
where the Z boson is produced with a high transverse momentum.
High transverse momentum. Okay, now you've lost me.
Think of it this way. If you hit a billiard ball head on,
Okay.
it'll move straight ahead, right?
Yeah.
But if you hit it off center,
Okay.
it'll also move sideways with some momentum.
Right.
That sideways motion is like transverse momentum in particle collisions.
Okay, I'm starting to follow you.
Yeah.
So particles with high transverse momentum are kind of like those billiard balls that got whacked sideways.
Yes.
They might be a clue that something interesting happened in the collision.
Precisely.
Okay.
Those high momentum particles are more likely to have come from the decay of heavier, potentially undiscovered particles.
Ah, I see. So by focusing on these high momentum Z bosons, they're narrowing down their search to events that might hold clues to new physics.
Exactly. Sneaky.
It's like looking for a lost contact lens.
Okay.
You don't start searching the whole house.
Right.
You start where you think you might have dropped it.
Okay. Yeah.
So they're applying that same logic to particle physics.
I love it.
Yeah.
It's brilliant. So they created these graphs of Z boson events
Right.
and then tested them out on both a classical computer and a photonic quantum computer.
Yep.
What happened next?
That's where the real test began.
Okay. Don't leave me hanging.
They looked at how well each approach could differentiate those potential new physics events from the background noise of standard model events.
Okay.
Remember, it's all about finding those rare, unusual events.
Right, like finding a needle in a haystack.
Exactly.
Or maybe a new particle in a mountain of data.
There you go.
Did they find any of those whispers?
That, my friend, is what we'll uncover when we delve into the nitty-gritty of the results.
All right, you've got me hooked.
And trust me, it's worth sticking around for. All right, so we've got our particle collisions, all neatly organized as graphs,
We did.
and we're ready to unleash the power of quantum computing on them.
Right.
Expert speaker, give me the aha moment. Tell me they found something incredible.
Patience, my friend. We've got to break down exactly how they tackled these graphs, both with classical computing and the more exotic Gaussian boson sampling.
Okay, fair enough.
Yeah.
But don't leave me hanging. What did they actually do with the graphs?
They use these graphs to create something called feature vectors.
Okay.
Think of these vectors as a way to summarize the key characteristics of each graph.
Okay.
Things like how many nodes it has, how connected they are, that sort of thing.
So they took something visual and complex, a graph, and turned it into a more abstract mathematical representation.
Exactly.
Why? What's the advantage of that?
Because computers, and especially quantum computers, excel at working with those mathematical representations.
Yep.
It's much easier to analyze and compare those vectors than to wrangle with the graphs directly.
That's fascinating. It's like translating a book into another language.
Right.
You might lose some of the nuance, but the core message is still there.
A very apt analogy.
Wow.
And in this case, the core message is whether a particular collision event deviates from what we'd expect from the standard model.
Right, those whispers in the hurricane.
Exact.
So how do these feature vectors actually help us find those deviations?
They fed those vectors into a machine learning technique called k-means clustering.
Okay, and what is that exactly?
Imagine you're sorting a box of buttons.
Okay.
You might group them by color or size, right?
Right, yeah.
K-means clustering does something similar with data points.
So they're grouping similar collision events together based on their feature vectors.
Exactly.
That makes sense.
And here's the key. They train the algorithm on a set of background events, the normal stuff we'd expect from the standard model.
So they showed the computer a bunch of ordinary collisions and said, this is what boring looks
You
like.
got it. Then they fed it the feature vectors from both the classical and quantum analyses, including some events they thought might be more interesting.
Okay.
The idea is that any event that doesn't fit neatly into the boring clusters might be worth a closer look.
Oh, okay, so it's like sifting for gold.
Right.
You have to wash away a lot of dirt to find those precious nuggets.
Now here's where it gets really interesting.
Okay.
They found that both the classical and quantum approaches were able to successfully identify potential new physics events.
Wow, so both methods worked.
They did.
Does that mean there's no advantage to using the quantum approach?
Not so fast.
Okay.
While both methods showed promise, the quantum approach actually outperformed the classical one in terms of accuracy.
Interesting.
Yeah, it was better at separating the potential new physics events from the background noise.
This is huge.
Like,
It suggests that quantum computers might be able to uncover hidden particles that traditional methods would miss.
precisely.
Wow.
It's still early days for this type of research.
Right.
Remember, this is just one study.
Okay.
And they used a relatively small data set
Right.
because simulating these quantum computers is incredibly computationally demanding.
Right. We talked about that earlier.
We did.
But the fact that the quantum method showed improved performance is incredibly exciting.
Absolutely.
It hints at the amazing possibilities that might open up as quantum computers become more powerful.
Exactly.
It's really exciting.
Oh, yeah.
So, are there other advantages then to using photonic quantum computers for this type of research?
Absolutely.
Like what? Tell me more.
Well, for one, they operate at room temperature.
Okay.
That might not sound like a big deal.
Yeah.
But many other types of quantum computers require extremely low temperatures to function,
Right.
which is a huge technical challenge.
So photonic quantum computers are a bit more low maintenance?
In a way,
Yeah.
yes. They're also incredibly fast at generating those Gaussian boson samples.
Okay.
Remember, we were talking about the sheer volume of data produced at the Large Hadron Collider.
Oh, yeah. It's like trying to drink from a fire hose. Way too much information coming in at once.
Exactly.
Yeah.
To keep up with that data deluge, we need analysis techniques that can operate at lightning speed.
Right.
And that's where photonic quantum computers have the potential to really shine.
So they could analyze the data in real time as those collisions are happening.
It's definitely within the realm of possibility.
That would be revolutionary.
Imagine being able to flag potentially interesting events immediately.
Yeah.
Rather than having to sift through mountains of data later,
Wow.
it could dramatically accelerate the pace of discovery in particle physics.
That's mind-blowing. But before we get too carried away, I have to ask, what about the limitations?
Of course, yeah.
We've touched on the fact that simulating these quantum computers is still really difficult.
It is.
What are some of the other challenges?
One of the biggest hurdles is scalability.
Okay.
The researchers in this study were limited by the number of qubits, those quantum building blocks of information they can simulate. To tackle more complex problems and analyze even larger data sets, we need to be able to build and control quantum computers with many more qubits.
So it's like trying to build a bigger, better Rube Goldberg machine.
Right.
The basic principles are there, but the engineering gets more challenging as you scale up.
Precisely.
Okay.
And then there's the question of error correction.
Okay.
Quantum computers are notoriously finicky.
Right.
Even the slightest disturbance can throw off their calculations.
Like a butterfly flapping its wings and causing a hurricane. The quantum butterfly effect.
Something like that.
Wow.
We need to develop robust error correction techniques to ensure the reliability of these quantum computations.
Right, because a wrong answer is worse of the no answer when you're talking about unlocking the secrets of the universe.
Exactly.
Yeah.
But despite these challenges, the potential of quantum computing for particle physics is undeniable.
Okay.
This study is just one example of how researchers are pushing the boundaries of what's possible.
This has been incredible. They took this incredibly complex problem, found an elegant way to represent it,
Right.
and then used a completely new type of computing to tackle it. That's what I call a deep dive.
It's a perfect example of how interdisciplinary collaboration, bringing together expertise in physics, computer science, and engineering, is driving innovation in this field.
It's like they're assembling a team of superheroes to decode the universe.
I like it.
So what does the future hold for quantum computing and particle physics? Are we on the cusp of a new era of discovery?
Yeah.
So we've talked about this incredible potential and the very real challenges, but what does it all mean? What does this research tell us about the future of particle physics, our quest to understand the universe?
That's the million-dollar question, isn't it?
Right.
And like any good mystery, we're just starting to piece together the clues.
Okay, I'm on the edge of my seat. Give me the most exciting possibility. What's the dream scenario here?
Imagine a future where quantum computers are so powerful that we can simulate particle physics models with mind-blowing precision.
Okay.
Simulations that go way beyond anything we thought possible with traditional computers.
Okay, so instead of just smashing particles together and seeing what happens, We could create these virtual universes to test our theories, like a giant customizable sandbox for physicists.
Exactly.
Oh, that's so cool. We could tweak the parameters, explore different scenarios,
Right.
and gain a much deeper understanding of how the fundamental forces and particles interact.
That's incredible. It's like going from sketching rough drafts on a napkin to creating high-definition 3D renderings of the universe.
Yeah.
What else can we hope for?
Remember those feature vectors we talked about?
Yeah, the ones used to identify anomalies.
Exactly. As quantum computers evolve, we might be able to develop even more powerful machine learning algorithms that can analyze massive amounts of data
Right.
and find subtle patterns that would have been impossible to detect before. Oh, wow. So we could discover new particles or forces just by analyzing existing data in a completely new way.
Exactly. It's like finding a hidden message in a painting just by looking at it from a different angle.
Wow.
The information was always there, but we needed the right tools to see it.
This is blowing my mind. But there's more, right? Didn't you say something earlier about designing better experiments with quantum computers?
Absolutely. Imagine using a quantum computer to simulate how different experimental setups would perform,
Okay.
taking into account all the complexities of quantum mechanics.
So you're saying we could actually optimize the experiment before even building it?
You got it.
That's incredible. Talk about efficiency.
It would be like having a crystal ball that lets you peek into the future of particle physics research.
Oh, wow.
You could see which paths are most likely to lead to groundbreaking discoveries.
Okay, I am officially on board the quantum hype train, but let's step off for just a moment and talk about the here and now.
Okay.
What are some of the more immediate benefits we might see from this research?
That's a great question. And brings us back to something we discussed earlier. The sheer volume of data produced in particle physics experiments.
Yeah, it's overwhelming.
Right.
Yeah.
Even if those aha discoveries are little ways off,
Okay.
the tools being developed today could have a real impact right now.
So even without discovering new particles, quantum computing could help us make sense of the mountain of data we already have.
Absolutely. Quantum computing offers more efficient ways to process and analyze that information,
Okay.
even if we're still using classical algorithms in conjunction with quantum systems.
So it's like getting a turbocharged engine for our data analysis while we wait for the rest of the quantum spaceship to be built.
A very apt analogy.
Here we go again.
And that's what makes this area of research so compelling.
Right.
It's not just about the distant future of particle physics.
Okay.
It's about using cutting-edge technology to make real progress in our understanding the universe today.
Well said. This deep dive has given me so much to think about.
It's fascinating stuff.
It really is. Yeah. It seems like we're on the brink of a new era in physics, and quantum computing is our key to unlocking these incredible discoveries.
I tend to agree.
Well, thank you so much for joining me on this fascinating journey.
Anytime.
Until next time on The Deep Dive.